Fundamentals of a neural network. This presentation is going to cover 4 aspects. First, we're going to introduce the neural model. Then we will discuss the single-layer neural network. And after that, we will introduce the 2-layer neural network. And finally, the multi-layer neural network. The study of neurons has a long history. As early as 1904, biologists has already understood the structural composition of neurons. A neuron typically has multiple dendrites, which are primarily used to receive incoming information. There is only one axon that has many axon terminals to transmit information to the other neurons. The axon terminals form connections with the dendrites of other neurons, thereby transmitting signals. The connection is referred as a synapse in biology. In 1943, psychologist McCouch and mathematician Pitts, referencing the structure of biological neurons, published the abstract neuron model known as the MP model. A neuron model includes input, output, and computational functions. The input can be categorized analogized to the dendrites of a neuron. The output can be compared to the axon. The computation can be linked to the cell nucleus. The input signals of the MP neuron computation model are weighted and summed, and the output is generated through an activation function. So the output y is equal to the activate function of the weighted input plus the bias. The typical activation functions include step function, segmod, and ReLU. The step function is non-differentiable and was used in early models. Segmod comprise the input to the range of 0 to 1. They are easy to differentiate. And ReLU resolve the gradients vanish problem of the segmod function. In 1958, computer scientist Rosenblatt proposed a neural network consisting of 2 layers of neurons. He named it the perceptron. The perceptron was the first artificial neural network capable of learning. Rosenblatt demonstrated its ability to learn and recognize simple images, causing a sensation in society at the time. People believed that they had discovered the secret of intelligence. Many scholars and research institutions began neural network research. The U.S. military heavily funded neural network research and considered it more important than the atomic bomb project. This period lasted until 1969 and can be seen as the first peak of the neural network development. Perception model has 2 layers, the input layer and output layer. The input unit in the input layer are responsible for transmitting data but do not perform any computations. The output unit in the output layer are responsible for computing based on input from the previous layer. The layer that performs the computations is referred as the computational layer. A neural network with one computation layer is called a single-layer neural network. A single neural network contains only one output layer that directly performs linear weighting and nonlinear transformation on the input. For binary classification problems, the sign function is commonly used. The learning process happened over the multiple iterations episodes, one data sample at a time. The learning process including the 4 steps. The first step is initialization, which initialize all weights to small random numbers. The second step is for the present one training example, which consists of a set of input and its true label target. Since it's a binary classifier, the true label D is either 1 or 0. Sometimes labels are represented as +1 or -1, which simplifies the weight update rule. The third step is to calculate the actual output. This is the weighted sum of the input plus the bias. This can be written as Z is equal to sum of the weighted weights multiply input. Then activate function throws Z into a step function to get the perceptron's prediction. So if Z is above 0 or is then therefore the output is equal to 1. But if Z is less than equal to 0, then Y is equal to 0. Step 4, calculate error and update weights. This is the core of the learning process. The perceptron compares its prediction output Y with the true value labeled D. So the error is equal to D minus Y. And the weights are only updated if the perceptron made a mistake. If the perceptron is correct, the error is 0. Therefore, the weights are already good for this example. If the perceptron is wrong, update always using the perceptron learning rule. The perceptron learning rule is that if D is equal to 1, but the perception predicted value is equal to 0, then therefore the error is equal to D minus Y is equal to 1. The rule becomes the new weight is equal to the old weight plus eta, which is the learning rate, multiply 1 and multiply input xi. This increases the weighted sum Z for this input, making it more likely the output will be 1 next time. If the true label D is equal to 0, but the perception predicted is equal to 1, therefore the error D minus Y is equal to -1. The rule becomes the new weight is equal to the old weight plus eta multiply -1 plus multiply xi, the input. This decreases the weight sum Z, making it more likely the output will be 0 next time. The bias W0 is updated too, using x0 is equal to 1. The weight 0 is equal to old weight W0 plus eta multiply D minus Y multiply 1. Then move to the next training example in the dataset and repeat step 2 to 4. When passing through the entire training dataset, is called an approach. The algorithm continues for multiple approaches until a stopping criterion is met. There are 3 criteria for the stopping. 1. All training examples are clarified correctly. 2. The error rate doesn't improve significantly. 3. The predefined maximum number of approaches is reached. So let's look at the example. For example, if we want to train a perceptron to learn the logical OR function, the training side we have 4 samples. One is x1 is equal to 0, x2 is 0, and the output should be 0. 2, when x1 is equal to 0, x2 is 1. The correct answer should be 1. 3, when x1 is to 1, x2 is to 0. The output should be 1. And 4, when x1 is to 1, x2 is equal to 1. The right answer is 1. Let's label using +1 represents true and -1 represents false. So when the value is 0, 0, x1 is to 0, x2 is equal to 0, that should be false. When the x1 is to 0, x2 is to 1, that should be all function value should be +1, which is true. When x1 is equal to 1, x2 is equal to 0, the value should be 1 +1. When x1 is to 1, x2 is to 1, the value should be +1. Let's initial the weights for W0 is to 0, W1, W2 also equal to 0, and the bias x0 is always to 1. And we set the learning rate eta equal to 0.1. For the first approach, when we see the sample 1, which is x0 is to 1, x1 is to 1, x2 is to 0, x1 is equal to 0, x2 is equal to 0. The d value, it should be -0. When we use z is equal to W0, which is 0 multiply x0, 1, plus W1 multiply x1 plus W2 multiply x2. So the value is equal to 0. The y, using the output y with the sign function 0 is equal to +1. In comparison with the true value d is equal to -1. So this value, this process is wrong. Therefore, we need to update the weights. The new updated weights should be the old the weights plus eta multiply d -1 multiply 1. Therefore, the W0 is changed from 0 to -0.2, and W1 and W2 still as 0. When the sample 2, when the x0 is 1, x1 is 0, x2 is 1, the true value should be +1. The z value is -0.2 multiplying 1 plus W1 is 0, multiply x1 is 0, plus W2 0 multiply x2 1 should be -0.2. The sign -0.2 is equal to -1. So in comparison with the true value d equal to 1, so the answer is still wrong. Then we still need to update the weights. After updating weights, W0 change to 0, W1 change to 0, and W2 change to 0.2. With the third example, x0 is 1, x1 is 1, x2 is equal to 0. The true value d should be plus 1, and the z value is equal to 0, and the y as the output of the 0 should be plus 1, that is equal to the d, so that is correct. There is no update. After this one approach, the model still make errors. The process continues with more approaches until it correctly classifies all samples. The final weights will define a line that separates the point 0, 0 from 0, 1, and 1, 0, and 1, 1. The perceptron resembles a logic regression model and can perform linear classification tasks. The weights in perceptron are obtained through training. The classification of effect can be visually represented by a decision boundary. In two-dimensional data space, this boundary is a straight line. In three-dimensional space, it's become a plane. In n-dimensional space, it magnifies as an n-1 dimensional hyperplane. So the perceptual learning rule is then the new weight is equal to the old weight plus the eta multiply y minus output O multiply x. For linear several problem, the algorithm is guaranteed to converge. Minsky pointed out that a single-layer neural network cannot solve the XOR problem. However, with the addition of computational layer, the two-layer neural network not only resolve the XOR problem, but also exhibit excellent nonlinear classification capabilities. Nevertheless, the computation of such network posed significant challenges due to the lack of efficient solutions. In 1986, Rumelhart, Hinton, and others introduced the backpropagation algorithm, which effectively addressed the high computational complexity required for training two-layer neural network. This breakthrough ignited widespread research interest in two-layer architectures. In 2006, Hinton published a paper in Science introducing the concept of deep belief networks. For the first time, unlike traditional training methods, deep belief network incorporate the pre-training process that enables the neural network weights to efficiently converge to a near optimal values. This is followed by a fine-tuning technique to optimize the entire network. The combination of these two techniques significantly reduced the training time for multi-layer neural network. He coined the term deep learning to describe this new approach to train multi-layer neural networks. Soon after, deep learning demonstrated remarkable potential in speech recognition. In 2012, it achieved groundbreaking success in image recognition. Hinton and his students used a multi-layer convolutional neural network to train 1 million images across 1,000 categories in ImageNet computation and achieved a classification error rate of just 15%. This result outperformed the second-place term by nearly 11 percentage points and conclusively proved that the superior recognition capabilities of multi-layer neural networks. The multi-layer neural network consists of an output layer, one or more hidden layers, and one output layer. Each layer comprises multiple neurons. Information is transmitted between these neurons through connection weights. The primary objective of multi-layer neural network is to achieve advanced data analysis and processing by learning the features and patterns inherent in the input data. The incorporation of hidden layer between the input and output layer endows the network with powerful nonlinear mapping capabilities. A single hidden layer is capable of forming open and closed convex decision boundaries. The double hidden layer, able to construct decision boundaries of arbitrary complexity through combinational effects, thereby solving any intricate classification problem. The multiple individual neurons are connected to form a multi-layer feed-forward neural network. This specific type of fully connected architecture is also known as a multi-layer perceptron. The forward propagation data propagates forward layer by layer from the input layer till the output result is obtained. In the mathematical equation, it can be written as the input for the linear through the linear combination is the input of the L-1 level A multiply the weights of the level L plus the bias, which will equal to the input of the hidden layer, and the output of this hidden layer is through an active function. The objective function for the optimization is to minimize the loss function. The loss function, usually the mean square error, is used to evaluate the network performance. The backpropagation includes 4 steps. The first step is to compute the output layer error. To calculate the gradients of loss function with respect to the weighted input. So the error is equal to the y minus O. And the dot denotes the element-wise multiplication. The second step is called the backpropagation error to the layer L. Using the chain rule, the error at the layer L can be computed from the error of the layer L plus 1, which is the error of layer L is equal to the weight of L plus 1 multiply the error at level L plus 1 and the element-wise multiplication of the differential partial derivatives of the active function to the ZL. The error is propagated backwards through the transpose weight matrix scaled by the derivatives of the active function at the current. Step 3 utilizes the error signal to calculate the gradients of the loss function with respect to the parameters. Then, we can update the weight parameters in the direction opposite to the gradients to minimize the loss. For example, if we have a single layer neural network, x1, x2 are input values, and there's a weights, and the hidden layer input h, and finally the output y. Suppose This example does not include the active function. The corresponding value x1 is equal to 0.5, x2 is to 1.0. The ground truth value of this is the donated y is equal to 0.8. And this one, first we initialize the weights using these random variables. As we can see, the forward propagation computational neuron output, the h1 is equal to the weight multiplied x1 plus the w2 multiplied x2. The h1 is equal to 1.0 and h2 is to 0.95, and the y output is based on this calculation is 2.9. So the error is a 0.8 minus 2.1 squared multiply the 0.5 is equal to 2.025. Then we calculate the partial derivatives. And we can see the partial derivative of the error delta to the y is equal to 2.1. And the partial derivative y to the w5 is equal to 1.0. And the error to the w5 is 2.1. And the error to the w1 is to 1.05. And the backpropagation using this equation, the weight is updated using the w5 minus eta multiply partial derivative of the delta equal to w5. Then we can obtain the new updated w5 is equal to 0.79, and the updated w1 is 0.895. By changing these weights into it, then we can see, we recalculate the process, we can see the delta value is decreasing.